So let's talk about the electrostatics of the space charge region today. All right, just a quick recap of last time. Remember last time the last thing we did was we found a way to calculate the built-in potential. Okay, there's two ways of doing it. One way was to use the energy band diagram and to figure out the amount of bending in the band diagram. That gives you the built-in potential. The other way is simply to use this formula. And actually at the end of class last time we saw that the two ways of finding V0 are basically equivalent. Okay, now what we're going to do today is go over the electrostatics, or the physics of the depletion region, because everything interesting that happens in a diode is mainly due to the depletion region. Okay, quick recap: the depletion region forms between the P and the N parts of a semiconductor. This side is P-type, this side is N-type. Holes diffuse from left to right, and electrons diffuse from right to left. When these carriers diffuse, they leave behind immobile charges. These are boron ions, column 3 ions that have a net negative charge when the holes leave that area. And these red circles are column 5 ions, like arsenic, that have a net positive charge when the electrons diffuse out of that area. The fact that you have positive charges and negative charges next to each other means that you have something like a capacitor. Okay, you have a positive buildup of charge one end, negative buildup of charge on the other end, so you have an electric field pointed from right to left, pointed from the red circles to the black circles. So we're going to calculate what that electric field is today. We're going to calculate what the charge densities are, and ultimately we're going to calculate, find a way to figure out the built-in potential and how it is related to the width of the junction.
So my question is, so why won't the holes and electrons neutral with each other?
What was the question again?
Why don't the electrons and the holes neutral with each other?
Why do they not neutralize each other? The electrons and holes in which region? You mean out here?
It goes to different directions, right?
Yeah, so what happens is the holes are diffusing from left to right. So as the holes diffuse from left to right, then they find themselves in the N-type semiconductor. And they will recombine in that region. So the holes are diffusing this way. Remember, they diffuse from high to low concentration. Right? But they're diffusing from a P-type material to an N-type material. When the hole goes to a region where there's a lot of electrons, there's a high probability that that hole will recombine. So the hole does recombine here. So your question was, do they neutralize each other?
The holes.
Yeah, the recombination is basically the neutralizing each other. The holes diffuse to the right side and they recombine there. The electrons diffuse over to the left side and they recombine there.
So there will be less holes.
There'll be less holes.
Less holes and less free electrons.
There'll be fewer holes and fewer electrons. That's correct. Just in this region here. That's why this is called the depletion region. The reason why this is called the depletion region is because this region is going to be free. There's not going to be any holes in this region. There's not going to be electrons in this region. So this region is depleted of carriers. Okay, that's what the depletion approximation says. Last time in class we ended up with this concept, so I would like to continue from there. Space charge equality tells us that the number of positive charges, number of positive ions on the right side of the junction is equal to the number of negative ions on the left side of the junction. Now both sides will have a different doping density. Okay, so if there's a high doping density on the N side, for example, there's going to be a high concentration of those arsenic ions. If there's a higher concentration of arsenic ions on that side, then these positive charges are going to be squeezed, the number of positive charges will be squeezed into a smaller area than the opposite side. So the example that we're looking at here is where the N side has a higher doping than the P side. So this would be referred to as an N plus P semiconductor. let me just jot that down. So just some definitions. So an N plus P junction, this means that the doping on the N side, Nd, is greater than Na. Na is the doping on the P side of the junction. In a P plus N junction, the doping on the P side is greater than the doping on the N side. Okay. So just to make sure that we all are all on the same page, in this example that's shown on the slides, we're looking at an N plus P junction. So in this N plus P junction, you see that the positive charges are at a higher density, meaning the spacing between the positive charges is smaller. This is true if you have a higher doping density on the N side. The number of charges, however, have to be equal to each other. So if these positive charges are squeezed into a smaller area, that means that the length of the depletion region on this side is going to be smaller than the length of the depletion region on the other side, because there's more spacing between the negative ions on this side because it has a lower doping density. Does that make sense? Okay, I see a few shaking heads. Remember this this picture here. Okay, every arsenic ion. Every arsenic ion that you donate into the lattice, you will create one positively charged ion, right? The higher the doping density of arsenic, so if this side is highly doped, you're going to have these red circles at a very high density. There's going to be a lot of those arsenic ions. And because the density is high, since a number, well, let's assume that the density here, density of positive ions is large, so the spacing between these red circles will be small because you have a high doping density. Assume that the doping density on this side is less, the spacing between these black circles, or the negative ions, is going to be more. So in that case, you can see that in order to maintain space-charge neutrality, the length of the depletion region on this side would have to be larger than the length of the depletion region on this side. Okay. If you can always rely on the mathematical definition also. The mathematical definition of space charge equality is simply this. Nd times xn0 is equal to Na times xp0. This is the amount of, let me back up here. This was the amount of positive charge on the right side of the junction. So the number of positive charges here, this is a formula for that. The number of negative charges on this side, this is the formula for that. The charge conservation law says the two must be equal to one another. So if you set these two values equal to one another, and you'll see that the Q's and the A's cancel out, you're just left with Nd xn is equal to Na times xp. All right, so this is an inverse relationship. Whichever side has the higher doping will have the smaller width. For example, if the doping on the P region has twice the doping of the N region, so if Na is equal to 2Np, or Nd, sorry, this should be Nd here. Let me fix that real quick. So if the P side has twice the doping density of the N side, then what's going to be the ratio of Xp and Xn? Which side is how small? What's the size of the depletion region on the P side compared to the N side? 1/2. That's correct. If one side has twice the doping density, then it has 1/2 the width. Okay, that's basically what this formula is telling us. It's always good to remember rules of thumb. All right. In this particular example, the N side has a higher Nd is much larger than Na. So X sub N ends up being smaller than X sub P. All right. So let's now go to the equilibrium behavior of the depletion region. So we're going to get into the electrostatics of the depletion region. So we've gone over some of these concepts already. Okay, the total charge can be found by integrating the charge density over the length. We did that at the end of class last time, finding formulas for the total positive charge and total amount of negative charge. Okay, now whenever these positive charges and negative charges are next to one another, this builds up an electric field. The electric field always points from positive to negative, so the electric field is pointing from right to left. So we're going to actually calculate what those specific quantities are. So this graph shows the charge density. You can see that the charge density is positive on the right side of the junction because you have these positive ions, and it's negative on this side of the junction. The plot of the electric field, qualitatively, it reaches a maximum. Notice that the electric field is negative. Negative because the electric field points from right to left. That's why the electric field is negative. The maximum electric field is achieved right at x equals 0. We'll talk about why that's the case. Okay, you reach a maximum electric field here, and then it decays to 0 as you go to here. It decays to 0 as you go to x sub p. So the electric field ends up being 0 outside the space charge region. Okay, the only region where you get an electric field is in the depletion region, or the space charge region. Okay, so to derive some of these relationships, deriving where the electric field comes from, deriving where that 0.6 volt potential comes from, we can talk about some basic concepts in electromagnetics, or specifically electrostatics. Have any of you taken ECE 4800? A couple of you? Okay. So it's a challenging class, right? You learn about these concepts in electromagnetics. We're going to cover just a few of them here. So the way that I like to describe this relationships between voltage, electric field, and charge, I like to describe it using a mechanics analogy, because that's something that you may be familiar with from physics. So in physics, in your whether you took it here or you took a class, advanced class in high school, you guys learn the relationship between displacement, velocity, and acceleration. So the velocity is the derivative of displacement, right? The velocity is equal to dw dt. Right? Displacement is meters. If you take the derivative of meters, so you take the derivative of displacement with respect to time, you get meters per second. That's velocity. You take the derivative of velocity, you get acceleration. So how many of us remember that? Okay. All right, good. We're all on the same page then. So acceleration is the derivative of velocity. So if we have acceleration and we want to figure out, and we want to go in the opposite direction. So let's say we have acceleration and we want to figure out velocity. The opposite of taking a derivative is taking an integral. Right? So the velocity is going to be equal to the integral of acceleration with respect to time. Now, just a detail, when you are taking an integral like this, when you're trying to find the velocity, the limits of integration are going to be from t equals negative infinity to time equals t. This will give you the velocity at time t. Okay, just remember that this lower bound of the definite integral is going to be infinity. Similarly, if you want to go from velocity to displacement, you take the integral again. So w of t is equal to the integral, again you have the negative infinity here to time t, of v of t dt. All right? So again, displacement to velocity to acceleration, take a derivative when you're going down these quantities. And if you want to go up the chart, if you want from acceleration, if you want to find velocity, take the integral once, take the integral again to find displacement. So this similar concept works with electromagnetics also. Okay. In this case, at the top of the chart is voltage. There you go. At the top of the chart is voltage. Middle of the chart is electric field, and at the bottom is charge. So if you know the voltage and you want to find the electric field, E of x is equal to dV dx. You're taking the derivative with respect to space. Now keep in mind it's with respect to space, not with respect to time. And you also have this negative sign here. Take the derivative of electric field, and you will get a charge density. Okay, and you also have this 1 over epsilon factor that you have to consider here. This is the permittivity of the material. So what we're going to be doing in this analysis is that we have the charge density. We have the charge density, and now we're going to find the electric field, and then from there we're going to find the voltage. So we are going to go in the up direction. Okay, we have the charge density in this case. So we are going to figure out electric field, and then you'll see later that we're also going to figure out the electrostatic potential. All right, so we need to go up on this chart. So from charge density, if we want to find electric field, we can take 1 over epsilon. The integral, again, you have this negative infinity here to x of the charge density. Okay, so one integration gives you the electric field. Another integration of E of x now gives you the voltage. And you have this negative sign that you have to make sure that you include there. All right, so it's analogous. You know, so the things we do in one engineering discipline is often similar to what we do in another engineering discipline. All right, so let's get down into the specifics of it then. So the electric field is 1 over epsilon, the integral from negative infinity to x of rho of x. Let's do that step first. So I think it's worth it to just understand this concept. The integral of negative infinity to x rho of x dx. Okay. Oh, let me move this down. So what we're going to do right now is we're going to figure out, we're going to derive the, so we have rho of x, E of x, and V of x in the depletion region. Okay, so let me just redraw the PN junction here. I think this will work, yeah. So this is the P-type material and N. Let's call this N plus. So this means that the doping on the N side is larger than the doping on the P side. This is the interface here. And so the depletion region on this side begins here. The depletion region on the P side is going to be longer than that, because of that relation that we just talked about, the space charge neutrality. So we're going to line up the charge density plot. That's going to be the one we'll do first. So this x equals 0, this is defined as the interface between the two materials. That's x equals 0. So this is our x-axis, and the first plot we're going to do is rho of x. So this is the charge density. All right, so when we're talking about charge density, number of charges per centimeter cubed. And we've already done this before, so this is a good starting point. There's a bunch of positive ions here, so we're going to have positive charge density here. And then there's a whole bunch of negative ions here. Okay, so that's why we will have a negative value in this portion here. All right, and what we assume is that once the depletion region ends, the charge density immediately goes to 0. So it's like a step function like this. Okay. Now in reality, there's going to be a little bit of curvature to this. It's not going to be a straight drop-off, but this is a good approximation. So the value here is Q times ND, and the value here is negative Q times NA. This is Q plus, the area under the curve, Q minus. All right, we've already established that those two areas are equal to one another. Q plus equals Q minus. Now, the next part here, we're going to figure out the electric field. So let's put down a chart here like this. The reason I'm drawing the chart like this is that I know the electric fields are going to be negative. So I'm just making sure I have enough room on the negative axis here. We can say E of x. All right. Now, let me just drag this thing down here. So the electric field is equal to this formula. E of x is equal to integral from negative infinity to x of rho of x dx. So what does that mean? Integral means we're looking at the area under the curve. All right, so when we take the area under the curve from negative infinity to some point x, another way of saying this is that the E of x is the area under the rho of x curve from negative infinity to x. All right, so we have like sort of a more qualitative, I would say intuitive definition of this. Okay? So, if I'm here, if I'm at this point, what is going to be the area of under the curve? Everything to the left of this. So the curve is this this blue line here. I'll just redraw it in blue. Red here. The curve looks like this. So what's the area under the curve? Everything to the left of this point. 0. Do we agree? Everyone agree that the integral up to that point is 0. So when we're drawing the electric field plot, let's just, come on, there you go. So the electric field line, everything from here to here is going to be 0. Now, what about in this region? What's going to happen as we go from negative x sub p? So this is negative x sub p, and this is x sub n. So what's going to happen as we go from negative x sub p to here? Yes, Andrew? So let's say, for example, let's say we're at this point here. Okay? If we're at this point, we have to take the integral of everything to the left, the area under the curve of everything to the left of this. Right? As we continue on to the left, we're going to integrate even more of this area. Right? Just delete that then. So what ends up happening is that as we go from here to here, the amount increases, keeps on increasing, keeps on increasing, keeps on increasing until we get to this point here. Okay? Now if you want to think about things in mathematical terms, the integral of a constant, what's the integral of a constant? A line, right? The integral of 2 is 2x, right? Okay, so the integral of a constant value is a line, so we actually have a line. If that constant happens to be negative, then the integral is a line with a negative slope, right? So that's why we have a line with a negative slope here. Now, what's going to happen as we continue this way? So what's going to happen, let's say I'm here at this point. So I'm going to include all the area on this portion here, but then I'm also going to start including some of this area here. You see? So I'm now summing up all the area at this point. I'm also summing up all the area here. Okay. This area was negative because it was under the y-axis. This area is positive because it's above the x-axis. So what's going to happen now is that the integral is going to start to increase. Again, if you want to think about this as a mathematical formula, you have a constant value here, and that value is positive. So the integral of a constant positive value is a line with a positive slope. So the value starts to increase like this. And it actually increases until we get to x sub n. All right, let me just... Here, let's delete this area, this stuff here. Okay. So this is going to increase right until we get up to about x sub n. And at that point, it's going to just continue on to 0 like this. Okay. Why is it 0 out here? If I'm out here, if I take the integral of everything to the left of this, so let's say I'm at this point here, I want to take the integral of everything to the left of this. Exactly. So we're going to have, if we're at this point, and we're going to take the area of everything to the left of it, we're going to include this positive area, and we're also going to include this negative area. The two are going to cancel out, yes?
The area is supposed to be equal, because the way you have it drawn, it seems like the negative is a little bit larger.
The areas are equal. Yeah, that's why I put this, I put this up here, because my drawing skills aren't great. As you can see, you probably realized by now, there's a reason I'm an engineer, not an artist. But I hope you can follow along. All right, so basically, how do I undo? I think there's an undo. There we go. Yes. I'm still getting used to this. Okay. Just bear with me here for a sec. There we go. What is it doing? All right. I'll just switch over between the two. Maybe it'll reset itself. Yeah, so this is x sub n, and this is negative x sub p. All right, so we have a plot for the electric field right now. Okay. This maximum value, just shown on the chart here, the electric field, the maximum electric field occurs at E of 0. So if we just plug in the value 0 here, okay, this was the general formula of E of x, 1 over epsilon integral from negative infinity of x of rho of x. So if we plug in 0 for x here, then we'll basically get the entire area under this curve here. Okay, and we already found out earlier that this was q times a times x sub p times na. All right, I'm sorry. Yeah, that's correct. But we don't multiply by the a. We only multiply by the a if we're trying to find the total charge. Okay, if we just integrate the charge density here, we get this formula over here. Okay, q over epsilon xp0 times na. Okay, so the maximum electric field occurs right here. The electric field reaches a maximum here, and then it decreases as we go to the right half of the junction. Now, intuitively, this should make sense. Okay, you build up a bunch of positive charges and negative charges right next to each other. The maximum electrical field will occur right in the middle, because you have the maximum effects from all the positive charges and all the effects from the negative charges. So the maximum electric field is at epsilon 0. The other important concept is once you go outside the depletion region, the electric fields drop to 0. Okay, they're all concentrated in one region. Okay, now the next step is finding the voltage. All right, so V of x equals integral from negative infinity to x of E of x. All right, so let's draw another thing here representing V of x. Now, we're going to do things in a similar way. Okay, we're going to integrate the electric field function. So again, the same thing happens when we're anything beyond negative x sub p. The integral, the area under the curve of E of x is going to be 0 here. So let's draw this. This is going to be 0 here. Now, what we're doing is we're taking the integral of a line. What happens if we take the integral of a linear function? What type of function do we get? No, not quite. So let's say, what's the integral of 2x? X squared, right? The integral of a linear function is a quadratic function. Okay, so as we integrate this function, we're going to end up getting a quadratic relationship. Okay, notice also that we have this negative sign here. So if we took the integral of this, this would give us a negative value, right? Because it has a negative slope. But since we have this negative sign attached to it, that the two negatives will make a positive, and that will create a positive parabolic function. So it will look something like this. It's a parabola. Okay, and this part here, if we continue to integrate it, we have notice that the area under the curve is all negative here. Okay, there's no sign change as there was up here. This area under the curve was negative and this was positive, but you can see that in this case the area under the curve is always negative. Right, so there's not going to be a sign change. It's going to continue on this parabolic trajectory like this, except it's going to be concave down, and then it will just smooth out like this. So this green line that you see here is the integral of this linear function, this blue line that you see up here. This difference here, this is your built-in potential. Remember, we defined built-in potential V0 as the difference in potential from the left side of the junction versus the right side of the junction. Okay, and just by using some basic electrostatics, we started from the charge density, we figured out what the electric field was, the relationship for the electric field, and then from here we figured out we integrated again and found the electrostatic potential. So the difference in voltage from this side to this side is equal to V0. Okay, this is a qualitative description of it. Now the actual formulas for it are shown on this slide here. This is showing the same thing. I just drew it out step by step so you can see. The electrostatic potential is the integral of E of x. Okay, V of x is equal to the negative integral from negative infinity to x of E of x dx. So at x sub n, the electrostatic potential at x sub n on this side of the junction, okay, if we plug x sub n here, and we take this formula here for the electric field, we'll find that the voltage at x sub n is equal to W over 2 E sub 0. Okay, so what this gives us yet another formula for the built-in potential. Okay. Let's recap a little bit. We found, remember, last time at lecture, we found that the built-in potential was equal to the curvature of the energy band diagram. Then we found a formula for the built-in potential. Right here, KT over Q, ln of Na ND over Ni squared. This formula is in terms of doping, okay? Doping Na and doping Nd. So the electrostatic potential is entirely determined by the doping. Now here we found yet another formula for the built-in potential. But notice that the built-in potential here is in terms of the width of the junction, xp0, Na. Right? So this time, now we have a formula for the built-in potential in terms of the dimensions of the depletion region. So if we set those two built-in potentials equal to each other, then we can find out what the dimensions of the depletion region are as a function of the doping densities, Na and Nt. And that's what we're doing in this slide. So we have formulas for the electric field and the voltage in terms of W, xp0, and xn0. So we can calculate each one of these dimensions as a function of doping. So the first thing is to use the charge conservation formulas to relate xp0 and xn0 to the total width. Okay, remember the total width of the junction is the width of the junction on the P side plus the width of the junction on the N side. This is the space charge neutrality rule. Na times xp is equal to Nd times xn. We can combine those to get these relations here. Just simple algebraic manipulation. So the second step is that we plug these in to the formula for VO from the last slide and solve for the width W. Okay, so on the previous slide, we found that V0 is equal to W over 2, Q over epsilon, xp0, Q, and A. Right, this is what we found using our analysis of the electric fields, by integrating the electric fields. So what we're doing here is we are substituting a value for xp and we're putting this in terms of the total width of the junction. Okay, so we're using this formula here. And by plugging this in, we get a formula for the width of the junction as a function of the built-in potential and as a function of the doping. So in your homework problems, when you're asked to find the width of the junction, what you'd first do is you'd solve the built-in potential. Okay, I give you the doping, you have to find, let's say I give you the doping, I ask you to find the built-in potential and the width of the junction. The first thing you do is find the built-in potential, so you solve for this part of the formula. Then you already have the doping, Na and Nd, so plugging these three factors into the formula, you can find the width of the junction. Once you have the width of the junction, you can then find Xp and X sub n using these formulas here. And that's what's being done in step 3. So you can solve for Xp0 and Xn0 in terms of doping. So these are the formulas for it. Okay. One thought exercise I would like you to do is try this on a sheet of paper. Okay, what happens to these formulas? So we're supposed to do an example problem on the next slide here. Let's see if we get to that. Before we do that, I'd like you to just try this thing. What will happen to W? Let's say Na is much greater than Nd. What will happen to this formula? Actually, you might not. You don't even need to do it on paper. Just tell me what the formula looks like. That's correct. So if suppose Na is very large, okay? Suppose Na is much larger than Nd. Which of these two terms is going to be significant? 1 over Nd, okay? If this thing is very huge compared to this one, this term is going to disappear. And you're left with just 1 over Nd. The width of the junction is going to be entirely determined by the doping on Nd. Okay? So, rule of thumb to remember, write this down. The properties of the junction, the width of the junction, and the properties of the junction are determined if you have what's called a one-sided junction. All the properties of the diode are determined by the doping on the lighter doped side. So I'll just write that down. So in the case of a one-sided junction, so what is a one-sided junction? If you have N plus P or P plus N. So one side has a much higher doping than the other side. In the case of a one-sided junction, virtually all the properties of the junction are determined by the doping on the lighter dope side. So in the case of an N plus P junction, it'll be the doping on the P side, or Na. In the case of a P plus N junction, it'll be doping on the N side, Nd. Okay. And those things are basically coming out of these formulas. So what does this formula simplify to? Suppose Nd is much greater than Na. What does this formula simplify to? Oh, sorry?
Square root 2 EV 9 over Q.
Well, let's just focus on this part here.
Oh, that part. Oh, okay. I mean, that looks like it was just one. Yeah, okay. Looks like it was one, right?
D is way big, right?
So if ND is very large,
So if you take the 1 over ND, so the NA will cancel
If energy is very large,
to be 1 over ND.
that's correct. It'll be 1 over ND. That's right. So basically, again, the doping ends up being determined by the lighter dope side. Okay. So moving on now, calculating the depletion characteristics. You have a homework problem that's virtually identical to this example problem that we're going to do here. So just to save some class time, I'm going to have you do this homework assignment, do this as a part of your homework assignment, so we're not doing it twice. Because this one will take some time to do, and I don't want to take the rest of the class period to finish this. All right, so what you're asked to do is suppose you have a step PN junction with NA equals 10 to the 18th, ND equals 5 times 10 to the 15th. So what type of diode do we have here? Is it a P plus N or an N plus P?
P plus N.
P plus N, right? P plus because the doping on the P side is larger than the doping on the N side. This is the doping on the P side, Na. This is the doping on the N side, Nd. Draw a plot of the charge density, electric field, and the voltage, and in the plot include the numeric values of charge, E sub 0, the built-in potential, and the dimensions of the depletion region. So chances are you will have some type of question like this on the exam. You'll be asked to figure out the width of the depletion region, find out the maximum electric field, interpret the plots of electrostatic potential, electric field, or charge density. Okay, you can count on having a problem like that. So also keep in mind that I could also give you a problem on an N plus P junction, where the N side has a higher doping than the P side. So in that case, you should be able to draw the charge density, electric field, and electrostatic potential plots in both cases. Fair enough? All right. Okay. So that's enough about the electrostatics of the depletion region. At this point, you should be able to, if I give you the doping for a diode, this side has this doping, this side has this doping, you should be able to tell me a lot about the diode. You should be able to draw the energy band diagram. You should be able to draw the built-in potential. You should be able to calculate the dimensions of the depletion region. You should be able to calculate the maximum electric field, okay, and figure out charge densities and so on. A lot of things you can figure out just from the doping of the diode. So that, everything we've discussed thus far is the behavior of the diode at equilibrium. Does anyone remember what equilibrium is, how we defined it before? What's that? No change in concentration. Stimulus. Think about it in terms of stimulus. Equilibrium is no stimulus. So all these things we derived about the depletion region and the behavior of the diode were under the assumption that there's no stimulus. Equilibrium, no stimulus. Okay. This is a chart of transient, steady state, and equilibrium. Just a little bit more detail than what we had on the previous module. Under equilibrium conditions, if we look at this chart here, we talked about Jn drift plus Jn diffusion is equal to 0. Jp drift plus Jp diffusion is equal to 0. There's no currents in the diode at equilibrium when there's no stimulus. Again, I mentioned this in the class last time. If the diode was able to generate current on its own, then we'd have an infinite source of energy, right? So obviously, there's no net current in the diode. At equilibrium, the carrier concentrations do not change with time. What we're going to be looking at now is the steady state condition. So this part here. Under steady state conditions, remember, steady state stimulus is being applied. A DC stimulus. So, in other words, we are applying a voltage to the diode. Alright, so this analysis basically has to do with, you have a diode like this, and we just apply a voltage to the diode. So we can redraw this diagram since now we know what's inside of a diode. There's going to be a depletion region here, a depletion region here, and what we're doing is we are applying a voltage between the two sides of the diode. Okay, so this would be forward bias. So let's say it's a steady state analysis. Okay, in one case, if we apply a positive potential here and a negative potential here, the positive potential is being applied to the P side of the junction, the negative potential is being applied to the N side of the junction. This is referred to as forward bias. If we do the opposite, so if we apply a positive voltage to the N side of the diode, this is referred to as reverse bias. So we're going to study how the diode behaves under forward bias as well as under reverse bias. And starting with this picture here, we have this voltage that's applied to the junctions. And what we're going to try to understand is what does the energy band diagram look like? At forward bias and reverse bias. The other thing we're going to ask is, what are the carrier concentrations? What are the carrier concentrations? At forward bias and reverse bias. And then finally, what are the currents? Okay, so that's what we want to do. We want to really understand the physics of the diode at forward and reverse bias. So another thing I want to know, does anyone remember what we've looked at this before, right? The relationship for a diode, the voltage and the current. What is the voltage-current relationship in the forward bias? It's exponential. Yeah, that's correct. That's correct. So it goes up like this in the forward bias. In the reverse bias, it's basically a small negative value here like this. Okay. So where does this IV characteristic come from? That's what we're going to talk about. Okay, in the context of the physics of the diode. All right, so that's this next part of the discussion here. We'll spend the next 20 minutes on that. All right, just to go over again, steady state is the case where stimuli is constant, so we're applying a fixed DC voltage to the device. There's no buildup of charge anywhere, so carrier concentrations do not change with time. dP dt, dN dt is 0. So this slide is basically showing the IV characteristic for a PN junction and what the polarity of the voltage is. Basically just what I just showed you in the drawing. To understand this exponential relationship, we have to look at the actions of the majority and minority carriers in the device. The majority carriers in a p-type semiconductor, the majority carriers would be holes In an N-type semiconductor, the majority carriers would be electrons. Now, when we're talking about diodes, if we have a P plus N device, the majority carrier is the holes. If we have an N plus P device, the majority carrier is the electron. Okay, just so we have our terminology straight. So it turns out that this exponential IV relationship is very important in circuits. Does anyone know where diodes are used? Where do we take advantage of this exponential IV characteristic? Sorry? Sometime, well...
Reverse batteries?
What's that?
Reverse batteries.
Reverse batteries? Yeah.
Circuits.
Yeah, sometimes we take advantage of the fact that the diodes have a 0.7 volt bias. Sometimes we use it as a battery. Another thing we do is that we can take advantage of the fact that diodes conduct current only in one direction. They're essentially a one-way device. Notice that the current is positive; it's never negative. So current really only flows one way through the device. Does anyone know where we take advantage of the one-way current of a diode? What are some examples? AC adapter, right? In voltage rectifiers. Voltage rectifiers rely on this one-way current propagation. Another place is in radio detectors. Diodes are used in AM radio detectors, amplitude modulation, AM radio. They're also used in nowadays in electrostatic discharge devices. So some of you, if you've done electronics lab, you've probably run into this problem where you burn out a chip by touching your finger to it because your finger has a lot of charges built up into it. Well, there are electrostatic discharge protection circuits that use diodes. So when the charge in your finger, if you have like a lot of positive or negative charge on your finger, and that deposits itself into the device, the diodes will actually carry away that charge from the circuit to prevent it from burning out. Okay, so there's a lot of places where we leverage this exponential IV characteristic and the fact that diodes really only conduct current in one direction. We'll talk about later that if you go to a very large reverse bias, you can actually get some reverse current. That's called reverse breakdown, but we'll get to that later. Let's just try to understand this portion of it first. All right, so let's first talk about the forward bias, the energy band diagram. So the rule that we use when analyzing the energy band diagrams, the difference in the energy band diagram before we drew that band diagram, one of the things that we said was that the Fermi level is constant. Okay, it's a horizontal line. There's no slope to it. That rule applies at equilibrium. When we are in forward bias, when we're at reverse bias, now the Fermi levels can actually change. Okay, we talked a little bit about this in the context of the first module. Let's see if I can bring that up here. Module 3. If you recall this, the last thing that we talked about in Module 3 was the energy band model of drift current. And one of the things we said was that if you place a voltage across the semiconductor, whichever side has a higher voltage will have the lower Fermi level. Okay, so in this case we applied a voltage to an N-type semiconductor. The positive voltage was placed on this side, negative voltage was placed on this side. The Fermi level, the corresponding Fermi level in the energy band diagram is lower on one side and higher on the other side. Okay, and the way that we rationalize that is that the electrons, if you have a negative voltage here, the electrons are going to want to drift from negative to positive. Right? That's what electric current is, drift current. So the electrons on this side have a higher electrostatic potential than the electrons on this side. They want to move from high to low electrostatic potential. So the way that we rationalize that in the energy band diagram is that we draw a slope in the band diagram, and the electron that's in the conduction band here would go from higher to lower energy states. The conduction band is filled with energy states, and the electron is progressively hopping to lower and lower energy states as it's propagating through the semiconductor from right to left. Okay, so coming back to this module now, the same rule applies. In the forward bias, the Fermi levels in the two regions are separated by an energy equal to the applied potential. Whichever side you place the forward voltage on, so for example, if we place a positive voltage on the P side of the junction, as is shown in this diagram, remember these battery diagrams, like whichever side has the longer line, that's the positive potential, the smaller line is a lower potential. So this P side is at a higher voltage. This side has a lower Fermi level. Okay. Notice that we've drawn two Fermi levels in this case. We've drawn a Fermi level on the P side of the junction and a Fermi level on the N side of the junction. Okay, and they are separated. The distance between these two Fermi levels is equal to whatever voltage you applied. So let's say you applied 3 electron volts, or let's say you applied 0.3 volts forward bias. Then the distance between these two Fermi levels would be 0.3 electron volts. Remember the difference in units. If we apply 0.3 volts to the device, the difference in Fermi levels here will be 0.3 electron volts. So if we do that, okay, what happens is that the energy barrier, this QV0 here that we talked about earlier, this now becomes smaller. It goes from QV0 to QV0 minus VF. You can see, because this is a book drawing, much better than my drawings, you can see that the potential barrier has reduced from this initial value at equilibrium to a smaller value when we've applied the forward bias to it. Okay, so as a result, applying VF reduces the energy potential between the P and the N sides. Now, thinking back to what happens at equilibrium, that balance between diffusion and drift, what do you think will happen if we reduce that potential barrier?
That would act like a short circuit.
It'll start to act like a short circuit. Why?
Because you're reducing that potential between the two sides, like in the diagram.
Okay, if we reduce that potential barrier, what's that going to, like, how are the carriers going to move?
More carriers are going to move into the conduction.
And the holes are going to move the opposite way.
Yeah, both of you are correct. Right, right. So Andrews is saying that that there's going to be more movement of holes in the conduction band because you've reduced this potential barrier. And Michael said that there's going to be more movement of holes in the valence band. I'm sorry, there'll be more movement of electrons in the conduction band, and then more movement of holes in the valence band. That's absolutely right. So this slide shows what's happening at equilibrium. You know, we drew the stack of electrons and holes here. Remember, the farther you go away from the energy, from the Fermi level, the lower your electron concentration. That's why we drew this as a stack, and the opposite is true for holes. So at equilibrium, there's a potential barrier that prevented the diffusion of these electrons, except maybe the highest energy ones. When we put this in forward bias, now we've reduced this potential barrier, so there's more diffusion of the electrons. The electrons are diffusing this way, the holes are diffusing this way. So that diffusion drift balance, at equilibrium we said electron drift is equal to electron diffusion. Hole drift is equal to hole diffusion. Now that balance is upset because diffusion is becoming more significant than drift. All right, and this energy band diagram is a nice way of expressing that. It's a good way of understanding that fact. This energy potential barrier is reduced. The built-in potential resists the ability of carriers to diffuse, and when you remove that barrier, reduces the energy difference, thereby enhancing diffusion. So diffusion is enhanced in forward bias. So let's do this exercise together. Forward bias, diffusion and drift. So diffusion and drift are both present, but diffusion becomes more prevalent than drift. The difference results in a net current from P to N. Okay? If the drift and diffusion currents were balanced at equilibrium, now they're unbalanced. If they're unbalanced, that results in a net current. Just hammer that point in here. At equilibrium, Jn drift plus Jn diffusion is equal to 0. They're equal to each other. So if you start increasing this diffusion, now you're gonna have a non-zero current. Same thing for holes. So you end up with a current. And in fact, we know that when we put a forward potential on the diode, we get current flow in this direction. Okay. All right, so going back now. So let's do this one together. What I would like you to figure out here, this is the energy band diagram at equilibrium and forward bias. And the charts here show particle flow, and it shows the corresponding current at equilibrium. So the first box here shows equilibrium. The second box here shows forward bias. It shows a particle flow and the corresponding current at forward bias. So what I'd like you to do just as a quick exercise is figure out which one is which here. We have 4 rows here, and the four possible mechanisms is electron drift, electron diffusion, hole drift, and hole diffusion. So I'd like you to figure out which one is which. Number 1, number 2, number 3, number 4. It'll be either electron diffusion, electron drift, hole diffusion, or hole drift. So take a minute and see if you can figure that out. So, any thoughts?
And 3 will be electron diffusion. I think it's 4.
What's that? Shall we?
I think 4 electron diffusion.
Okay, let's start with 4. Why is 4 electron diffusion?
So it's drift. The current is going against the particle. No, it's drift. I think it's 3. Yes, 3.
So we got the first part right. It is electrons. How do we know it's electrons?
Because of the direction of
Absolutely. Yes. Exactly. Exactly. So the current is in the opposite direction as the particle flow, right? So we know that it's electrons. So that's good. We're halfway there. Okay. Michael says it's drift. Also, we have some people saying it's drift. Why do we say that this fourth one is drift? We know just by looking at these 2 arrows, we know that it's electrons. By looking at these 2 arrows, we know that it's electrons. But how do we know that we're talking about drift current as opposed to diffusion?
Only diffusion because like bias. So
I think it's 3.
Yes, exactly. Diffusion is enhanced at forward bias. So we should be seeing a larger arrow at forward bias compared to equilibrium.
oh, the sizes are something too.
The sizes matter as well. Size matters. So you see that the magnitude of the drift currents are the same here as they are in forward bias. All right. But the diffusion currents, we're also talking about electron currents here because the 2 arrows are pointed in the opposite direction. But the arrows become larger in forward bias. So this is definitely diffusion. Number 3 is electron diffusion. So what is number 2?
Hole drift.
Number 2 is hole drift, right? particle flow and current are in the same direction, and there's no change, equilibrium versus forward bias. And the first one, by process of elimination, is hole diffusion. Particle flow and current are in the same direction, so we're talking about holes. And that mechanism of current is enhanced at forward bias. So this would be hole diffusion. All right, good. So we have about 6 minutes left. So this is something we're going to come back to next class. But I think it's a good idea to get started on it now, because this is there's a lot of notation here, and there's some concepts here, and it's helpful if you kind of see it once, and then you'll see it again next class period. So we're going to talk about the what happens to the carrier concentrations. All right, so we answered this question here. We talked about what the energy band diagram looks like at forward bias. Now we're going to talk about what the carriers are doing at forward bias, and what eventually we're going to get to what the corresponding currents are. So this slide is just representing all the notations that we will talk about. I added this in later because students were often confused when doing the homework assignments. What symbols mean what? So this is sort of a definition of that. Okay. So what we're going to do here is we're going to have a physical model for the PN junction. I'm going to explain it qualitatively in 5 minutes, and we're going to come back to it next class period. So this is an example of a P plus N diode. How do we know this is a P plus N diode? It has to do with depletion widths. How do we know this is a P plus N? Because the N region is wider than the P region. Right, that's correct. Okay, so we're going to look at carrier concentration. The way we're going to do this, we're going to make a chart here, a plot. Okay, on the right side of the chart we have X sub N. On the left side of the chart we have X sub P. And what we're going to plot is a minority carrier concentrations, N sub P and P sub N. Okay, N sub P means the electron concentration in the P region. P sub N means the hole concentration in the N region. So we're talking about the minority carrier concentrations. This is the minority holes on the N side, and this is minority electrons on the P side. So at equilibrium, we can plot these out, and you guys already know how to calculate these. Okay, if I give you the doping on the N side, you should be able to figure out the electron and hole concentration on the N side. And you should be able to do the same on the P side of the junction. So drawing these lines is no problem. This is what the minority carrier concentrations look like at equilibrium. Now the thing I want to impress upon you now is that what happens at forward bias. This is what happens at forward bias. This red line here. Okay. Why do you think this is happening? Think back to what we just talked about on the last slide about enhanced diffusion. We're enhancing the diffusion of holes from left to right. We're enhancing the diffusion of electrons from right to left. So how's that going to affect the carrier concentrations? It's going to increase it. Why? Michael?
Generation from the voltage?
Not from, well, the voltage is reducing the potential barrier, right? But how is this changing the carrier concentrations? Why do the carrier concentrations look like this?
The electric field.
Not because of the electric field.
When you reduce the barrier, they can move easier. Right?
You reduce the barrier, they're moving easier. So why is the hole concentration going up like this? Where are those holes coming from? From the other side. Exactly. Yeah, exactly. So think about, just picture this. This is plotting the hole concentration on the N side. This is plotting the electron concentration on the P side. So what's happening is holes are dumping over from this side over to this side, right? We're enhancing diffusion, so more holes are dumping over to this side. What happens when the holes dump over to this side? They recombine. Okay. Now, does this exponential relationship look familiar? Remember in the last module how when we were creating extra electrons and holes on one side, on the lighted side you had excess carriers, and those excess carriers diffused over to the other side and they recombined. We ended up with this exponential distribution, right? So this exponential distribution of holes are coming from the fact that you have these holes on this side that are diffusing over. When they diffuse over, they recombine. And that combination of diffusion and recombination generates this exponential profile. Basically, the hole concentration is increasing here. The farther you go away, more of the holes will have recombined by then. And so the hole concentration will go back to the equilibrium amount. Okay. Does anyone remember what factor determines how quickly this curve drops down? LP, exactly. Diffusion length. Diffusion length is the average distance a hole diffuses before it recombines. So if you have a large diffusion length, this will be a very gradual decay. If you have a small diffusion length, it'll be a sharp decay. Okay. So the same story holds for this side of the junction. Electrons dump over from the right side to the left side, and so you end up with an electron concentration here. One last question before we end for today. I forgot to ask this. Why is Pn0 greater than Np0? Because it's a P plus N. That's correct, Nasser. So whichever side, this side has a higher doping, right? So this has a very high hole concentration but very small electron concentration. Remember, the two are inversely proportional to one another. So this has a very low electron concentration on this side. This has a more moderate doping. Okay, so this is still it's N-type. There's a lot of electrons, but the minority carrier concentration on this side will be higher than the minority carrier concentration on this side. P plus N, whichever side, let me just state this succinctly, whichever side has a higher majority carrier concentration will have the lower minority carrier concentration. Okay. All right, we'll end with that. We'll come back to this on Thursday.